All right, I guess you can start. Hello, everyone. Welcome to Database Internals Meetup number 7. My name is Alexey Kopytov, and I'm excited to kick off today's meetup because it's special in many ways. I believe this is our second meetup online, but it's the first meetup in our series that is being held in English, as you might have noticed. And there are basically two reasons for that. The first one is that one of our speakers today is from China. He doesn't speak Russian. I'm going to introduce him shortly. But the second reason is that we would like to make the content of our meetups available to a wider audience, right? Over the past year, we've had many great talks and great speakers with deep technical insights into all kinds of database architectures. So we thought it's unfortunate that all of that great content is only available to the Russian-speaking community. It would be nice to share that knowledge and those discussions with the global database community. So this meetup is sort of an experiment for us, a pilot episode, so to say. Some hiccups are possible. Please don't judge too strictly. And by the way, the response to our announcements on social media was super positive and fantastic. So thanks to everyone who has responded and helped us promote the event. Now, a few words about questions. Of course, we're going to have some time for questions and answers at the end of each talk. You can ask your questions at any time during the talks. You can use YouTube, the YouTube chat, the video chat, or our Telegram group, whatever works best for you, okay? And then at the end of each talk, we are going to read those questions for the speaker, all right? Now, without further ado, I'm going to introduce our first talk and our first speaker today, Mr. Zhao Dongsheng. He's a founding engineer at Ape Cloud, and the Ape Cloud company is the parent company for the WeSQL project, which is what Dongsheng is going to be talking about today. Dongsheng, the virtual floor is yours. You can start.
Yeah, okay. Thank you. Okay. Okay. Hello, everyone. I'm Dongsheng Zhao, work as a founding engineer at Apple Cloud, and I'm in charge of the storage engine for WeSQL. Today, I will introduce WeSQL, an open source cloud native MySQL solution designed to run on the general purpose IaaS. WeSQL combines MySQL compatibility with the scalability and elasticity of modern cloud infrastructure, aiming to provide a powerful, cost-effective cloud database. Okay. Here is what I will cover today. First, I will talk about the background and the motivation why we built WeSQL. Then I will walk you through the overall architecture of WeSQL. After that, I will take a dive into some of the key technologies in WeSQL. Finally, I will look at some benchmarks and see how WeSQL compares with AWS RDS. Okay. Okay, let's begin by looking at the current state of cloud-native databases. Today's mainstream cloud-native databases typically offer several core capabilities. First, compute storage separation, which allow compute and storage resource to scale independently. This leads to better resource utilization and lower overall costs. Second, most architectures adopt a shared storage wide writer multiple reader model. The write scalability is usually achieved by scaling up the primary node, while read scalability is handled by adding more read-only replicas. Third, in recent years, serverless electricity has emerged as a key feature in enable compute resource to scale based on the workload demands. It's moving closer to true pay-as-you-go model. However, there are some also notable limitations. Most leading solutions today are offered by major cloud vendors and are closed resource and are closed source, which introduces the risk of vendor lock-in. Additionally, these databases typically rely on dedicated storage clusters. Aurora uses its own multi-tenant storage cluster. Socrates has a dedicated Xlog and Xstore. PolarDB is built on a distributed file system and store data in the PolarStore. While dedicated system offer flexibility and can be tailored for specific needs, they come with trade-offs, including high development costs, operational complexity, and it's difficult to open source because the storage cluster is dedicated and it's not easy to deploy. Okay. Given the drawbacks of current cloud native databases solutions, we set out to build something different. A cloud native databases that is open source, easy to deploy, and optimized for general purpose infrastructure like EBS, S3. There are two core motivations behind the WeCircle. First, we want to create a solution that is open source and MyCircle compatible. This ensures that users can adapt WeCircle with minimal changes to their existing applications. At the same time, open source means it's easier to deploy, operate, and integrate into a wide range of environments without being tied to a specific cloud vendor. Second, WeCircle is built to run efficiently on general purpose IaaS, unlike other solutions that rely on dedicated storage cluster. WeCircle requires no dedicated backend infrastructure. This makes anyone can deploy it on a public cloud, such as AWS, Azure, or Google Cloud, with standard components like EC2 and S3. And because of our architecture's choices, we are able to deliver a compelling cost-performance balance, reduce both storage costs and operational complexity. At the price, three factors that often trade off against each other. For example, local disks, NVMe SSD offers the lowest latency, ideal for operations that are sensitive to response time, such as index updates, transactions, and cache access. However, they lack built-in durability, and I tied to the compute node. EBS volumes such as AWS GP3 provide better durability and the persistence than the local disk, and offer relatively good latency. But the cost of per GB is significantly higher than the object storage, and they still come with operational limits or scalability and burst performance. Like the default IOPS of GP3 is 3000, and the bandwidth is 125 MB, and it does allow to modify a volume more than often once every 6 hours. S3 or other object storage service provide high durability at low cost and nearly infinitely scalability. The trade-off is the higher latency. Okay, make it unsuitable for latency critical workloads. This comparison lead you to an insight. Just no single storage solution can satisfy all requirements, like include the latency, durability, and price. Based on the trade-offs we just discussed, we make two critical architecture decisions when designing WeSQL. First, we introduced the persistence latency separation method for latency sensitive operations, such as writing logs, caching. We rely on local NVMe SSDs. These provide low latency. These provide low latency access at high IOPS, which are critical for ONTP workloads. For durable long-term storage, we use Amazon S3. It offers extremely high durability, low cost per GB, and elastic scalability. The design enables users to decouple compute from storage while keeping operational costs under control. Second, we choose a LSM Tree-based storage engine. The append-only write pattern of LSM Tree naturally aligns with the characteristics of object storage, like S3, reducing the random write and improving write throughput. Additionally, SM's multi-level architecture maps well to a tiered storage layout, making it possible to combine the memory, local SSD, and object storage. In short, this combination uses local disk for speed and object storage for durability, allow WeSQL to offer both performance and scalability without depending on dedicated storage cluster. Okay, now let's look at the high-level architecture of WeSQL. Circle layer, it's almost compatible with MySQL, including support for standard protocols, tools, and MySQL clients. And the middle layer, Raft-based replication plugin, write options are replicated across nodes using Raft protocol plugin. This ensures high availability and consistency without relying on dedicated storage clusters. And the low layer, smart engine storage layer, this is our storage engine based on MySQL plugin storage method, and I will talk it later. At the S3 based object storage, durable data and metadata are asynchronously flashed to S3. This decouples the durability from performance and enable infinitely cost-effective scalability. Okay. With this architecture, WeSQL delivers the performance of traditional systems, the elasticity of cloud native service, and the openness of MySQL ecosystem, all without relying on dedicated storage cluster. We can deploy it on the general purpose IaaS. Okay, let's dive deeper into Smart Engine, our LSM Tree-based storage engine, which is designed to run efficiently on top of object storage like S3. Here is how the write path works in Smart Engine. First, the incoming writes are first written to the WL for durability, and then stored in a in-memory structure called the mem table. When the mem table fills up, it is flushed to S3 as level 0 files. These are immutable sorted tables, similar to SS tables. Over time, background compaction process merge files across levels from level 0 to level 1 and then level 2, ensuring space efficiency and improved read performance. Okay, to support fast recovery and consistent reads, metadata snapshots are predictably synced to S3. These snapshots include reference to the latest manifest logs, WL, and data files, enable point-in-time recovery. In the read path, the query acquire a superversion first, which contains the current mem tables and the meta snapshot, which includes the metadata in level 0, level 1, and level 2. And the query looks up from mem table, catch level 0 to level 4 until finding the satisfied result. Okay. Okay, the follow I will talk some key technologies in WeCircle. First, one of the core technologies that enables high availability in WeCircle is our Raft-based replication plugin. 对, it's implemented as a plugin, so we can decrease the modification about being binary log. Okay, let's look at it how it works during normal operation. All writes go to the leader node. This ensures a single source of truth and simplifies the transaction coordination. So all transactions execute in the leader node. When a transaction is committed, the leader writes the binary log and replicate it to log nodes. These log nodes act as lightweight followers. The main job is to receive persist and acknowledge binary entries as quickly as possible. Once a quorum typically 2 out of 3 has acknowledged the binary log writes, the transaction is considered durable and committed. The binary log is then asynchronously uploaded to S3, ensure log time durability. Okay, this Raft replication model provides strong consistency and fault tolerance. Okay, in WeCircle's Raft-based plugin, failover is handled automatically. When the leader becomes unavailable, one of these loggers will be elected as the new leader using Raft's consensus holography. After becoming leader, it checks whether it has any binary log entries that the previous leader had not yet uploaded to S3. If so, the new leader will upload the remaining binary logs to S3, ensuring no data loss. Okay. Then a new data node will be started and transferred as a new leader. Then resume accepting writes through new leader. It ensures that the binary log is always complete and consistent, which is also critical for downstream tasks like point-in-time recovery, backup, or replication. In WeCircle, we've designed consistent snapshot mechanism that captures a full point-in-time view of database and store it all S3, which means all data of WeSQL can be stored in S3 consistently. Here is what's included in a consistent snapshot. The data dictionary data in InnoDB, and the user data in Smart Engine, and the full binary log history for redo and replay. Now, let's walk through the snapshot procedure. First, we start a snapshot task, which coordinate the process across all components. We temporarily enable a parameter called clone block DDL to block DDL operations and avoid inconsistent metadata changes. Uh, third, a snapshot of InnoDB is captured using MyCircle's clone plugin. The fourth, we then acquire a consistent snapshot place. This place consists of the binary log place from MyCircle binary log, and the WL place from Smart Engine, and the manifest log place also from Smart Engine. Once these places are recorded, we disable clone block DDL and resume normal DDL execution. The snapshot data stored in a local directory is then copied to S3 for durable storage. Any log files that are necessary to reproduce the snapshot state, specifically logs before the snapshot operation, are also uploaded to S3. Finally, we will update the snapshot index to reflect the newly captured consistent snapshot. Through this procedure, we can generate a consistent snapshot of WeSQL and store it on the S3. Okay. To further improve performance and reduce S3 access latency, WeSQL introduce a multi-tier cache system. It consists of 3 layers: row cache, block cache, and persistent cache, each targeting different types of workloads. Let's take a look at each one. The row cache, this cache stores frequently accessed hot rows in memory, allowing for ultra-low latency rates. It shares memory quota with the mem table, so we can dynamically balance between the write throughput and the read performance. The block cache, this is the main in-memory cache for Smart Engine data blocks. It supports multi-priority caching, where frequently accessed blocks get a higher priority, like the index block. And it has a cache pollution protects to prevent large scans from invocating useful data. Features like cache migration and cache warming help to decrease the stink of cache hit ratio during the flash or the comparison job execution. And the persistent cache, this layer uses local NVMe SSD to store recently accessed data, providing a fast intermediate tier between memory and S3. It supports both read-through and read-write-through modes. Yeah, and it's configurable. You can adjust the cache path and the cache size based on your instance local storage. And and it supports async parallel the recovery, meaning that even after failover or switchover after restart, the cache can be restored in the background, and it will not increase in the RTO because the RTO is critical for the serverless. Okay. Together, these three layers enable WeCircle to minimize the code as the S3 reads, speed up query performance, and reduce operational cost. Okay, and in WeCircle, we store data in hybrid row column storage model, which gets a balance between OLTP style row access and OLTP column efficiency. Let me explain how it works. We begin with a component called the schema sync, which receives schema definitions and helps determine how data should be laid out. Data is internal organized using a PAX layout, aka partition attribute across layout. Uh, each storage block contains a group of rows, but within each block, columns uh, are stored separately. This enable better compression and can serve OMTP style query within WISE-IO in most cases during cache miss. Okay, during compaction, the data is converted from the row format to column layout automatically according to the synced schema. And for the performance for the performance consideration in level 0, where the most recent the data resides, we retain row format for low latency point lookups. This format is also used in the blockheads, which accelerates read performance for hot data. Okay, and to speed up point queries and filters, we use a persistent Bloom filter stored alongside the data blocks. This helps avoid unnecessary S3 reads and improves cache hit ratio. This hybrid model, this hybrid data format model gives WeCircle OLTP responsiveness while maintaining compact, efficient storage footprint. Okay. Okay. Next, let's look at complex. This is a critical part of the storage engine that ensures the data is organized efficiently and remains performant over time. And it's important part in the LSM Tree-based storage engine. Okay, WeCircle's compaction framework is designed to handle various workload patterns and object storage constraints. It includes the following key features. First, multiple types of compaction task. We support background compaction, manual trigger compaction, and level-specific compaction. This allows the engine to adapt to different data patterns, whether it's bucket inserts or updates or steady write traffic, and we also do many work or the comparison scheduler, like the idle scheduler, yes, like the idle scheduling, to reduce interference with foreground read and write workloads. Compaction tasks are scheduled during idle periods. This improves the overall query latency and keeps the system responsive under load because through the idle scheduler, the LSM tree is more healthy, and it uh, has only Y level, so it can do little merge work during read. Okay. Third is the block level reuse. When compacting data, we identify and reuse existing blocks that have not been changed. This significantly reduces S3 writes and avoid redundant I/O, making compaction more efficient and effective. Through the block level reuse, we can reduce the computing work of the compaction task. Okay. The fourth and it's also important when compactor or S3 is the S3 I/O thread pool. Because since compaction include the computer data, just compacted data, and write the data to the storage. And in the local file system, we do the work in a single thread, and just first compact data, and then write it to the local file system. But the S3 latency is very high, and in this model, and will lead to the compaction speed is very low. So we implement a S3 IO thread pool. Yeah. This allows us to pipeline the computation at the S3 IO, improve compaction throughput, and minimizing latency. It's like the AIO. Yeah. Through these optimizations, make WeCircle's compaction engine work efficiently or S3. Okay, let's see. That's some key technologies in WeCircle, and at last we will see some benchmarks. First, in TPCC workload, we prepared the same scale of data on both platforms, or AWS or RDS using InnoDB. The dataset took up approximately 9.5 TB of disk space. Or WeCircle using its columns storage mode, the same data only required 785 GB. That's over 12 times smaller. What's even more important is that WeCircle stores its code data or Amazon S3. S3 provides much cheaper storage compared to EBS or local SSDs without sacrificing in the durability. This means drastically lower storage cost, especially for the large and the history data sets. Okay. And the other benchmark is the sequence OMTP read-write workload, and we compare it and we still compare WeCircle with AWS RDS MyCircle. We deployed WeCircle or the same EC2 instance type as RDS using M5D point X large. It has 4 cores, 16 GB memory, which is a common production setup. We prepared 100 tables, each with 2 million rows at tested performance under different levels of concurrency. The result, WeCircle achieved nearly 4 times higher QPS compared to RDS, with significantly lower latency. This highlights WeCircle's efficiency in real-world OLTP scenarios, especially under high load. And the critical why WeCircle can get so high QPS is that we can use the local SSD as a cache to accelerate the I/O. It has very low latency compared to the EBS. Okay. Okay, that's all. That's all my presentation. And
Okay, thank you, Dongsheng. Actually, we don't seem to have any questions. Come on, people, don't be shy.
okay.
But I have a few questions for you. Oh no, we actually have some questions on YouTube. So the question is, you used a multi-tiered cache system, which is expected, but that confused me that usage of local NVMe storage for persistent cache. How much does it add up to startup time of computing node?
Okay. Sure. It's a good question. We use the specific EC2 instance. Yeah, you can see every EC2 has a size with a local disk, like the M5 point X large, and it will have a size M5D point X large. And I think it's you should configure the persistent cache size according to your total data set. In our exercise under the ONTP workloads, I think I think the 12% of your total size can be satisfy most workloads.
Okay, thanks. Oh, there's another question from the same person. Also, it adds some cost for storage, but you showed that it's quite reasonable. Okay, it's not a question, it's a statement. Okay. Any other questions? Pavel?
Yes. Hi, I'm Pavel. I have a couple questions. First one, so it seems like you don't have classical row storage at all, right? So it's just you have small buckets of column stores, right? Or did I misunderstand it a little bit?
The standard engine support both row format and column format.
Oh, okay. I missed that. I thought you got these exceptional numbers just with the column store. And with the column store, so you also have a block or vectorized engine with all the SSD stuff, or do you just use the vanilla query engine?
The circle layer is same with MySQL. Okay.
Okay,
The column format in our smart engine, we use it to get a higher compression. Yeah, and decrease the cost. Sorry,
are you planning to add a special handling, special operators in the query processor to speed up analytical queries too, or?
Yeah, I think okay, it's a good question. And I think the multi-model is a is a good choice. And we have think to store the data in the like the dirt in the like in the iceberg and in the iceberg format, and we can query the data through some open source query engine, and we don't plan to implement ourselves. It's I think the open source has many good choice. Yeah.
Okay, got it. Again.
Okay, actually, Dongsheng, I also have a few questions for you. Actually, I have a lot of questions, but our time is limited, so I will only ask a few. You might have mentioned it, but I just want to double check. This LSM storage engine, smart engine, was it developed by Ape Cloud from scratch, or it is based on some open source implementation like RocksDB, for example?
Okay. Yeah. It has a long history. Yeah. A smart engine is not developed entirely from scratch by Apple Cloud, and it based on X Engine, an open source storage engine developed by Alibaba Cloud, and my X company. Yeah, which itself was the X Engine was originally derived from an early version of RocksDB. Yeah, and the X engine was designed specifically for OMTP workloads to serve Alibaba eco business, and it had been widely deployed across Alibaba Group and Alibaba Cloud PolarDB. And PolarDB had option PolarDB X engine. Okay. And I was one of the core developers of X Engine. So I was deeply involved in its design and development. At Apple Cloud, I was heavily refactored and extended the X Engine to adapt it to the cloud native architecture. Yeah.
Okay, thanks. So it's basically a heavily modified version of X Engine, which in turn is a heavily modified version of RocksDB. So in a way, Smart
Yeah.
is based on RocksDB, which I think
Yeah.
is great because we all know that developing a new storage engine from scratch is a huge amount of work. So it's better if it's based on something as proven and widely deployed and battle tested as RocksDB. Great, thanks.
Yeah. So,
Yeah, but as far as now, so it's not related to MyRocks, for example, which is another MySQL storage engine based on RocksDB. There's no relation between Smart Engine and MyRocks. Is that correct?
yeah.
Okay.
Yeah.
Okay, but for example, as far as I know, as you probably know, MyRocks compared to NDB has a number of limitations, like foreign keys are not supported in MyRocks, and the full text search indexes are also not supported. Does Smart Engine have the same limitation compared to NDB in terms of?
Yeah. Yeah. I think the specific Smart Engine support most InnoDB features, but not all. Like as you mentioned, the FTS or foreign key constraints. And what I want to say is according to our observe the user in the Alibaba Cloud, I think the most feature the user use the Smart Engine is support. Yeah.
Okay, I see. Thanks.
Okay.
So in terms of SQL level compatibility, are there any incompatibilities with MySQL? I mean, between WeSQL and MySQL. How easy or how hard it is to migrate MySQL applications to WeSQL?
Okay, that's a good question, and that's our user asked us before. Since Smart Engine is in place as a MySQL storage engine plugin, it's fully compatible with MySQL for the features it supports. Except the features we unsupport, like the FTS or foreign key constraint. As long as your application does not rely or these unsupported features, and you can migration transparently. Yeah.
Okay, I'm asking because usually like distributed databases have some limitations, like for example, select for update is usually not supported and so on and so forth. So it's good to know that migrating applications from MySQL is easy. And we still have some time. One more question from me, maybe. Actually, Pavel also has some questions. Pavel, go ahead.
Yeah, well, it's more of a final question actually, but I was wondering, so you have you introduced a lot of new ideas. I'm wondering, do you have publications, like some kind of like either scientific or kind of extended blog posts about the internals of WeSQL, and if you do, where can we find them? Yeah.
Okay. Okay. Let me.
Basically, the question is whether you have any scientific publications, papers, or do you plan to publish something like that?
Or maybe just technical, technical blog post with details. We can actually, I think we can add them to the meetup if you have something you want to share. We can add them
Okay.
to the videos. Yes.
Okay. We have not yet. We have some introductions on our website, and the detail of technical papers have not published. Yeah.
Okay.
Okay, and another question from me. As you probably know, there are open source implementation of object storages compatible with S3, right? So would it be possible to use WeSQL with those systems rather than infrastructure as a service, S3 compatible services?
Yeah.
Like I'm talking about Minio, for example, right? There's this popular open source implementation of S3 called Minio, and you can deploy it on-prem. Would it be possible to use VSQL with that system?
Yeah. WeSQL can run all the object storage if it compatible with S3. Yeah, and as now we have supported MinIO or R2 and the OSS in Alibaba Cloud. Yeah.
Okay, so it's not necessarily the cloud. You can actually use an S3 compatible system deployed on-prem, right? Which is great.
Yeah. That's our critical motivation, and you can deploy it with Circle or any vendor which provide the components like EC2 or S3.
Okay, great. Thank you. I don't see any other questions, right? So thank you, Dongsheng. It was a great talk. Thanks.
Okay. Thank you.
And now I'm passing the floor to Pavel, who will introduce our next speaker today.
Thank you, Alexey. It was a wonderful talk that you invited. It was very interesting. Our next talk is on a similar topic. It's about, so the first one was about cloud native database. Now we're talking about a serverless database, also built from an open source system, this time Postgres. And I'm happy to introduce Piotr Pleshachkov. He's a founding engineer at Nile, and he will talk about this new thing. And we have a lot of questions already batched up to ask him. Okay, so Peter, yes, please start.
Yes, please. Let me share. Can you see it?
Yes. Perfect.
Okay. Hello, everyone. My name is Peter. I'm a founding engineer at Nile. And at Nile, we are building a serverless Postgres dedicated for modern multi-tenant SaaS applications. So first of all, a few words about what is a modern multi-tenant SaaS application. It's actually applications which you all know and use every day. And for example, this is applications like Slack or Linear or Notion or Stripe, whatever. And so this is normally worldwide applications. And so how they work, that you can use them as an organization, and so you just register on that service as an organization, and then you use that application, and you have a feeling that you are an owner of this application. Like everybody uses Slack, so you have your organization which has an account in Slack, and then you have multiple users for your organization and data associated with that users. And so this organization is pretty much the tenant for the SaaS application Slack. And it's the same story for other multi-tenant applications. Most of the modern new applications, they are multi-tenant, so they are dedicated for multiple organizations for all tenants. Sometimes they are called workspaces, doesn't matter. So these applications, they are pretty much everywhere. All new applications are multi-tenant, but to build such applications, it's not an easy task. So all these applications, they have the whole stack of technology, but of course, the most challenging part is the data layer. So you have to store data of your tenants somewhere, and that's normally a database. And then when you have multiple tenants in your application, then of course you want to scale. It's a world, it's a global application, and you may have many tenants. It's like thousands of tens of thousands, so really a lot. And you would like to scale very well, and to make sure that it's cheap to add tenants to your application. And normally this is these applications, they're built on top of relational database, and currently the default open source database is Postgres. So building such applications is challenging, because tenants it should scale very well for when you add more and more tenants to your system, and then you have make sure that it's relatively cheap to do that. And today we'll talk about Nile and how we support tenants, and so that Nile gives you a built-in multi-tenancy into the database layer. So that's actually the first offering which is doing that. So normally multi-tenancy is built on top of databases, and that's the engineering effort of developers of the applications. It's not built into the system. So today we'll talk about the architecture of Nile and so how we built it. First, let's consider it on the example. Imagine you have a simple HR application, and you track all your employees, and so you have a simple table, employee number and employee name and salary. And this is a single tenant application. But then you have SaaS, human resources application. And in that application, you already have multiple organizations or customers or tenants. It's the same synonyms. So every organization has its own employees. So you have pretty much multiple databases, one database per tenant per organization. And then for the application developer, so there is a so the question how to model it actually. So what you will do with that, so there are two extreme approaches. So one approach would be to store every tenant in a separate physical database. So in Postgres, you can create a database and you store tenant in this database. In this case, eventually you will have thousands of databases. And this approach has its own advantages and disadvantages. So there are many advantages for that. So you can isolate your tenants pretty well. That's one of the key requirements for such applications. The data of one tenant cannot be leaked and seen by other tenants. That's completely different organizations. And if you suddenly leak a data to other tenants, it's just not acceptable. So you have to be very careful about that. And putting it in a dedicated database, it just gives you a natural isolation. The next advantage is that if you wanted to backup and restore data, it's quite often that you have a problem with a specific customer or with a specific tenant, and you have to restore the data to do something about it. So you can use standard Postgres tools to do that. Then, of course, you can profile, so you see where your tenant lives. So you easily can see the usage of resources for that tenant, and you can tune that resources. And of course, the next requirement that if the tenant should be placed in a specific jurisdiction, and then you can also do that, creating database in a specific jurisdiction. So but there are significant downsides of this approach. And so the main thing about it is that that's the cost of this approach. So creating a database, Postgres database per tenant, it could be too much. It could be too expensive. So the database comes with a significant overhead like buffer pools, like connections, and in Postgres connection, it's a backend process, so it's pretty expensive thing. Then if you have spikes in the usage of, so initially you customize your Postgres for specific usage, and if you have a spike, then it's not so easy to quickly adapt to that. So operational overhead in general, it's pretty high. So that's why normally multi-SaaS application developers they don't use completely this approach. Another thing is that when you split completely your data, your tenants, then you cannot easily support cross-tenant queries. So if you wanted to do that, again, you have to build it on top of Postgres in your own application. And of course, data migrations, that's also an issue because, schema migration, sorry. In this case, if you wanted to change some schemas in your application, like you wanted to add one more column to your employees table, it should be done consistently across all the tenants, all the databases. So it's a distributed transaction which should be done on top of Postgres in that application. Another extreme approach for supporting the multi-tenant applications is to add a tenant ID column to every table which you have. So in this case, you will distinguish the rows of your tenants on the logical level, but they will live all together in a single table, or if you have normally you have many tables in a bunch of tables, and that's another approach. It's much cheaper. It's much cheaper approach. So add a new tenant costs you almost nothing, But there are significant downsides as well. So the downside is that you expose then to the noisy neighbor problem. So if one tenant has a spike in the usage, doing some heavy operations, then other tenants will notice that. So then you will have unpredictable latency, and so the tenants will feel each other. It's very hard to achieve data isolation in this approach. So again, all the queries which SQL queries which are used in the application, they have to be very carefully reviewed that they don't leak any data of other tenant. So and the chance that you will make mistake and leak the data of other tenant, it's pretty high. The next downside is that per customer backups and restores, they're quite hard. So you can use standard Postgres tools, but then for the restore, you will have to, if you wanted to restore a specific tenant, then you will have just to see in the backup every tenant ID and to restore only that specific tenant. So that's from the operational point of view, it's really hard. And scaling out. So eventually, you will reach so many tenants that you will somehow scale out your system. But if you have everything in a bunch of tables, so it's very hard to scale. And of course, compliance issue if you wanted to have tenant data only in a specific jurisdiction. So that's a very important requirement that cannot be underestimated. So then it's also a very hard to achieve that. You have just everything in one place. And the typical query in this multi-tenant applications, it's actually normally specific for tenant. So, okay, you have these tables, but your SQL will, in 90%, will always go to the, will query specific tenant. So always you will specify the tenant ID because, well, the tenants, they are just logically isolated. So you don't want that tenant know even about each other. So in this sense, the typical workload it's quite local. So if you have data of your tenant on one machine, so then you normally don't have distributed queries. It's a local query, and the same for updates. However, you do would like to support cross-tenant queries as well, because normally this is needed for some reporting, for some analysis, for multi-tenant applications, for some combined usage and things like that. So sometimes it's for some aggregations. Sometimes it's very convenient to still have support for cross-tenant queries as well. But the 90% of the queries they are tenant specific. And how Nile addresses actually this challenge of supporting multiple tenants. So we considered two extreme approaches. One with database, physical database per tenant, and another extreme approach is that you put all your tenants like in a single database. And in Nile, we introduce a concept of virtual tenant database. It's not a tenant, it's not a physical Postgres database. It's much cheaper solution, but it's just a virtual database where you store the data of a specific tenant, and on physical database you can put multiple tenant databases. And so we try to combine the benefits of both approaches, single database and single table. So we try to store physically tenants, all tenants data isolated, but place them on a actually cluster of Postgres nodes. So we try to achieve that the cost per tenant is very low, but still we achieve the isolation of tenants from each other. So that's, as I mentioned, very, very critical. So placing it on the serverless distributed Postgres cluster, we just try to achieve low cost. So we don't put every tenant on a dedicated database. And let's consider the architecture. So Nile itself can manage multiple logical databases. And logical databases, that's a database which is created by a multi-tenant SaaS application. And in scope of this logical database, multiple tenants can live. So tenant and virtual tenant database, that's more or less the same in this presentation. And so here you can see that we put multiple, so we have here two Postgres instances, and we place two tenants on one Postgres instance, and yeah, we have tenant 3 on another Postgres instance. And that's actually another way how you can see Nile with a little bit more details. The entry point at Nile, it's a Nile gateway. So Nile Gateway, it's a proxy which implements a Postgres protocol. So Postgres protocol, and that's what the clients like PSQL, GDBC driver, or whatever use to work with Postgres. And so the clients think that they talk to Postgres, but actually they talk to Nile Gateway. And so that's the top layer. And under that layer, we have the cluster of computes. So we decouple the Postgres monolith into compute and storage. And we have stateless serverless computes. It's like a cluster of Postgres nodes. And that's where we, by default, put new tenants. But also, you can create dedicated compute or provisioned compute for highly demanding tenants. So when you put tenants on a all together on the compute, they still can share the resources of that compute, like for example buffer pool. And so if you would like to avoid that, and you would like to have a dedicated instance, then you can create a dedicated compute and use for that specific tenant. But normally in real world, you have many of tenants which are not really demanding, in terms of resource usage. So you can place them on existing serverless compute, and Now provides a pretty good free tier, so that you don't have to pay for that anything. If you use dedicated compute, of course, you do have to do that. And then the compute is a stateless part of Postgres. And then there are two other services like page server, which stores the pages, and the WAL service, which stores the WAL of Postgres. And the real data is stored in the S3. So from a Nile point of view, the page server serves only the data of a specific tenant. So potentially you may have multiple page servers, and we decouple compute and storage. Let's consider how you can create new tenant. So the Nile user will have to use existing built-in tenants table. So that's a Nile built-in table. It's called tenants, and you just insert a new row into that table. So what will happen when you run this insert? So the query will come to the Nile gateway, and what we'll do, we'll intercept that query and parse it, understand, okay, we are inserting new tenant, and we'll pick a random serverless compute and place the tenant on that compute. If you would like to put a tenant on a dedicated compute, then you specify that again in your query, and you place tenant on that specific compute. So using SQL, you can easily control what's going on when you put your specific tenant. And of course, this is a little bit simplified picture. So there are also regions. So you have we have we have multiple regions, and so, for example, one region in US, one region in Europe, and so you can explicitly specify not only the compute ID, so where you put it, but also you can specify the region where you wanted to put it. It's very important from the compliance point of view for multi-tenant applications. And then when you run your queries, it's very simple. So for the user, they see the tables for the application. So they still see that the tables are still, they still have the tenant ID column. So as I mentioned, we try to build a hybrid approach, and so you still have the tenant ID, but under the hood, the table, the Postgres table, which we call a tenant-aware table. It's under the hood. It's not a simple table, but it's a table which consists of Postgres partitions. So in Postgres, there is a concept of partition table, and so every table, every tenant is we put on the partition table. Okay, so that's just a little bit more details. But let's go back to our SQL. So if you would like to query only a specific tenant, then you set the Nile Nile tenant ID, and that's the ID of the tenant or organization. And then when you select something from the to-dos, then you will get rows only for that specific tenant. So it means that for the application, there is no need to filter out all other tenants. So setting this GUC, it's enough. So after that, you will get results only for that tenant. And of course, the magic happens on the Nile gateway. So that's the place where we'll understand, okay, we have this setting, and then we'll add this condition to the query. So pretty much rewriting the query. But you can explicitly do that as well. So to add the condition to your query, and then, okay, we also understand that, and that it's a tenant-specific query, and we will route it also to that specific tenant. So it's like a mechanism of not querying the whole big table with all tenants, but we then route the query to that specific tenant. And also we support cross-tenant queries. As I mentioned, it's not very common query in multi-tenant applications. 95% of queries, they are tenant-specific, but sometimes you still want to have that capability. And so if such a query comes, so we see that there is no tenant specified, that's a cross-tenant query, then we'll pick just a random compute, and then from that compute, the query will be distributed. And so you will get results for all from all tenants. So this is needed only for some administrative queries. So normally you will work with the specific tenant. And then the next important part of the architecture, how we move tenants. So why do we want to do that? There could be multiple reasons. So we considered that initially we placed a tenant either on serverless compute or dedicated compute, but eventually you will have too many tenants, for example, on your compute, and you wanted to rebalance your computes, and you wanted to move your tenant. That's only one use case. Or again, you would like to move your tenant to another jurisdiction. So that's quite common operation, and it should be done very efficiently. And at Nile, we do support this move tenant operation, and in our case, it's more or less like well, it's some Postgres specifics, but we detach the partition table from the root table, freeze vacuum, and then we so attach that partition and unfreeze on another compute. But that's just a move of metadata. So the real data, they are on the page server, and that's the procedure, like sort of reassigning the page server from one compute to another compute. So this operation can be done very quickly. Okay, and for example, you can use this if you have very demanding tenant, and so you would like to move it to the more powerful compute. So you provision your Postgres compute with more memory, more CPUs, etc. So then you can quickly move your tenant to that more powerful compute. So that's what we achieve with decoupling storage and compute. Okay, so summary. It's not. I will have a little bit more in my presentation, but just intermediate results. That so within Nile architecture, we support tenant isolation. So the actual data is separated. So we store tenant data on a page server, and actually on the Postgres level, on the Postgres page, on the Postgres block level, we do the separation. It means that all the tuples of tenants, they are stored together, and so they are not mixed on the block level. We efficiently support the tenant placement, so that and it's a controllable it's controllable where your tenant is. That's also very important. And so the tenant rebalancing, if you add more and more tenants and you wanted to scale out eventually, then it's also supported. But it's so one important thing is that you do have to do tenant rebalancing or adding more nodes only if really it's needed for the usage, because so sometimes if you, for example, you build your multi-tenant application using the DB per tenant, you will have to create more Postgres nodes, not because of that you have too much data, but because of the limitations of Postgres, like too many connections, or because of the architecture of Postgres. So that's pretty important. So you scale and you add more resources only if you really need them. And of course, splitting, decoupling the storage and compute, we can easily support on the tenant level. The advanced features like point-in-time recovery or branching. Branching, it's really important feature, so that in modern software development cycle, you normally have multiple branches, but on the data level, normally you don't. So you also would like to have branching on your data layer, and with Nile you have a capability to support branching per tenant level, and that's supported on the database out of the box. You also can monitor and the usage and performance of your system per tenant, and you also calculate the cost per tenant. So that's that's really crucial things which multi-tenant SaaS applications need to build efficient and to rely on to make it cheap, the data layer. And one more thing which I would like to mention is schema migrations. So schema migrations in managing multi-tenant applications, it's really a pain. So if you would like to add a new column to run in terms of SQL, any DDL, to create table, to drop table, to alter table, etc., then you have to apply it consistently across all tenants, and it should be done at the same time, and it should behave like a single Postgres. So and all the mechanics under that the tenants are distributed, it should be completely transparent for the application. So that's so when developers build multi-tenant applications, normally they have to care about it and build something on top of Postgres. So we do it at Nile. So what we are doing well, we use two-phase commit for this, and we introduce a transaction coordinator. How it works that we have a Postgres, and then we suddenly have a create table. We created an extension for Postgres. So Postgres, what's the beauty of Postgres? Then it's really extendable database, and you can add new functionality through the mechanism of Postgres extensions. So in the Postgres ecosystem, there are many different extensions, and of course we also use that mechanism. So for DDLs, we built our own Nile DDL extension, and it relies on the process utility hooks of Postgres, so that every step in Postgres, you can use these hooks and on any stage of your query execution, you can add your functionality. So and that's what we do. So when we see the DDL, so we intercept the DDL queries. We make request to transaction coordinator to distribute this DDL to other Postgres instances where the tenants reside. And of course, the most interesting part here is that how to make the commit atomic. And again, we heavily use the Postgres functionality. So when the user commits the DDL transaction, then Postgres emits the pre-commit event. And again, we intercept that pre-commit event and send a associated command to the transaction coordinator, which will prepare transactions, the associated transactions, participant transactions on other Postgres instances. And if everybody answers that, okay, I am prepared well, so then Postgres, so then the next event comes, and which is a commit. Then we do the commit prepared. And of course, if something goes wrong, in case of any crashes, then the transaction coordinator will make sure that the transaction is either committed or rolled back completely. So we guarantee that. So there is no possibility for partial results and things like that. Okay, so Nile, it's a relatively young startup, but we already have a system in production. So we have around 1,500 logical databases in production, and this is a database. This is not a number of tenants; it's number of apps which I use in Nile, and so we scale to thousands of tenants, and well, you can see other numbers. So our goal actually to be a default relational database for multi-tenant SASA, for multi-tenant applications, and so we make it cheap. We make it cheap to create virtual database for users, and that's on one side. So you can, on the other side, you can still isolate with our approach all your data, and built in the tenants concept into the Postgres database. So building multi-tenant, embedding multi-tenancy in the database, to my knowledge, it's the first database which is doing that. Okay, thank you.
Thank you, Peter. Yeah, really interesting stuff. We have quite a few questions in YouTube. So we have a few questions from Denis Smirnov. The first one is, what do you use for the page and write-ahead log storage? Is it something self-written from scratch, or is it Neon, or it's Fork? And do you write only write-ahead log to the storage, or also table index pages? Very.
Yeah. So the project of decoupling compute and storage, it's in progress. It's still in progress, so it's not fully complete. So we don't rely on Neon or things like that. So under the hood, for now we use S3. So as a page server, we actually rely for now on SlateDB, which natively supports S3, and the WAL service most likely will also rely on S3. So this is still in development, so some things can change. So we plan to finish it in 6 months. So after that we'll have more details. But for now we don't rely on things like Neon. It's not like that. So we rely on the SlateDB, which also uses LSM trees natively integrated with S3.
Got it. Okay. Yeah, and the next question is, can the tenants share the same Postgres database, and how do you isolate data in common tables like PG users? So like Postgres system tables.
Yeah. So indeed, the tenants they can live in different in the same Postgres. That's the idea, and how we do that. So we create a schema so they live under their own schemas, and yeah. So isolating on the PG catalog on that level, that's a separate project, and so that part is also not completely finished.
Okay, got it. There's well, you don't have to answer all the questions if you think they're or something about secrecy or commercial secret. The next question is it possible to move a tenant from one region to some other? And I think yes, right? So you answered.
Yes, yes. So that's the main thing, that you will be able to move it this way. Yes.
There's one more question. How big is the patch difference with vanilla Postgres? I don't. Yeah. I don't know.
Yeah. Again, so we tried to avoid forking Postgres as much as possible. So we built, as I mentioned, for example, for DDL, we built the extensions. So that's not forking; it's using API. But for decoupling, we do have to fork, and we try to make it minimal. It should be small. It should be small, but again, that's a work in progress.
Mhm. And so the next one is, do you make some additional parsing on the gateway side, or do you just filter page blocks per tenant on the page server? I guess during query processing, right? That's
We do have to parse. Yes, we parse query on the gateway. Yes, but the pages, they are separated on the page server.
Mhm. And yeah, the final question from Denise is, why do you need a transaction coordinator? Can't you just round robin tenants over serverless Postgres instances, or is this done for fault tolerance, for fallibility?
Yeah, this is done for schema migrations. So when you work with specific tenant, it's placed on a single Postgres, so no need for any distributed transaction. But if you want to change schema, you want to change it consistently across all your tenants, and they can be in even different regions. And that's where you have distributed transaction, and you have to make sure it's consistent. It's atomic and ACID.
Got it. Good. Yeah. One more question from Anthony Chapargin, I guess. What's the serverless compute in the scheme? Is it a virtual machine, or is it a pod in Kubernetes, or yeah?
Yeah, it's important Kubernetes. Yes.
Let's see. Let me check our chat. I think that's about all the questions folks wanted to ask from the internet. I have some questions too. Let's see. You're talking. So you have serverless compute and the dedicated. So in case of serverless compute, there's not. There might be no server at a given point to back it up. So what happens if you're monitoring your tenants, or what happens to latency if if the server is not provisioned at the moment?
You mean that your tenant is placed on the serverless Postgres? So
Yeah.
well, if and you need that you overload that node with too many tenants.
So I don't know, we might have different terminology, but we're also building a serverless database in Yandex with YDB, right? So at some point, if there's no usage, we can shrink the pool of compute nodes hypothetically to zero. But then when it's zero, then you start having all sorts of problems, like if you're monitoring. You can't monitor the database, and then latency becomes a huge thing because you need to provision a new server when a user actually decides to use it.
We don't shut down any serverless computes because it's cheap in our case, because it's normally in the systems where you have database per tenant, then it's pretty expensive, and then you shut down your pod or your database, and then you have a problem of cold restarts. and so high latency for first query. So Nile avoids that because tenant it's not mapped to the physical database. It's much cheaper.
So you're using through Kubernetes you get this right? Okay. And so when you're also next question from me is when you're branching, so you cannot do any per tenant schema changes, right? So the schema across all tenants has to be always the same, right?
Yes, schema should be consistent across tenants. Yes, but that's expected.
And when you're doing the move, you don't really have downtime. You might just have higher latency, right? But you don't.
Yes, so that's more or less like you lock your partition table, and then you move it, and well, you unlock it, and then so that's a magic inside of the Nile gateway that will redirect that request to the new destination when the move is finishing. But that's not a physical move. That's just moving metadata, and the real data they are still on the same page server. So it should be instant.
And what happens if your tenant, your single tenant, becomes too big for a single compute node? So even a big one. So are you planning to have kind of like a distributed version also of a single tenant database?
For now, we think so. We have the move tenant functionality, so we can provision more powerful instance. But so in real world, we don't see so many tenants, the single tenants that they don't fit into a single machine. So, well, if we encounter that problem, it will be a nice problem to have.
Okay. All right. Let's see. I just had one more question, but it slipped my mind. Let me check again the internet. Yeah, I think we don't have more questions from our audience. Oh yeah, yeah. So you still have that tenant ID in some cases, right? When you're sharing, when multiple tenants share a single machine or single database, you put tenant ID. But how hard is it to add this where condition? Because the queries could be complex. You could have like some crazy correlated subquery with some aggregations inside, and so you have to. Is it trivial, or is it pretty big, development to analyze the query and figure out where tenant conditions need to be added?
Well, we heavily rely on the Postgres tools for parsing and for analyzing. So it's reasonable effort to do that on the gateway for now. But of course, the architecture
on the queries.
the architecture. So internally, it's a little bit changing. It's done in a such so we are introduce the Postgres partitions, and the partition corresponds to the tenant. And in this case, you can route that query directly to that partition, and then you work directly with just tenant data, so you don't have to do that explicit filter routing.
Oh, so that's kind of a feature that's moving out. Yeah, you're switching.
Yes, it will be done in the future. Yes.
And yeah, the usual question is if you have any published kind of did you publish any papers yet? Are you planning to publish some technical blogs that we can?
We do. So there is a thenile.dev website, and there is blogs section where you can read, and also there is a YouTube channel. So our co-founder Gwen Shapira, she runs that channel where she explains the problems of multi-tenant applications and how we solve them at Nile. So we are pretty visible.
Okay, I will contact you later to add the links to our videos. And yes, okay, great. Okay, well, thank you. It was very, very interesting. Let me do the last checkup to see if there are any more questions. And okay, there's more. There's the last question from Denis. He's asking, how do you solve latency issues between zones? I guess between data center. Oh, yeah.
Between
I guess zones.
oh,
Yeah. So
the regions.
regions, yes.
Yeah. So as I said, most of the queries, they are tenant specific, so they are not cross regions. So if they are cross region, yeah, you will have to pay for the extra latency. We use the mechanism of foreign tables. It's a Postgres thing, so that if you have a foreign data wrapper, so then you can create a foreign table, and in this case, on every Postgres node, you can query any data across many Postgreses. It's like you easily get the distributed query implementation. But if you do across regions, of course, you pay for extra latency.
Oh, yeah, just a new question just popped up from Galina Antuzova. She's asking, do you have any automatic tenant rebalancing? For example, if some neighbors become noisy, can you automatically move a tenant to a safer place?
Currently, we don't, because we're on pretty early stage, but that's in our roadmap, and we are building infrastructure to do that pretty easy. So the move tenant operation, I talked about it. So we elaborated and work on it. And after that, yes, we definitely will do the rebalancing, because noisy neighbor, that's one of the significant problems, and with the built-in tenants support, we can solve it.
And just a final question from me. So yeah, you're continuing. So you'll have this limitation that the schemas of all tenant databases, that they have to be the same in the future, or are you planning to enable different schemas in tenants at any time?
Different schemas per tenant. Yeah, we didn't have such a request from our customers. So for now, it's not in our roadmap. It's not in our roadmap.
Oh, one more question. Is it possible to merge tenants? For example, one company buys another company, they want to merge the tenants.
Yeah, well, it's big. It should be big tenants, probably. I think in the future, of course, it would be possible. So for now, it's not in the roadmap to merge them. But well, it should be pretty straightforward to build it on top of our current infrastructure.
All right. Okay, well, thank you very much, Peter. Yeah, it was wonderful. Thank you all for coming to watch, and Also to people that are watching the recording, we'll add some links from the authors. And yes, stay tuned for our next meetups.
Thank you very much.
Thank you.